Hi everyone. In this video, we explore how to find the eigenvectors in the case that we know what the eigenvalues are. So we're supposed to know the eigenvalue lambda, and we'll try to look for possible vectors v that satisfy AV equals lambda v. That's the definition of an eigenvector. So if a certain vector satisfies this definition, I can rewrite that equality as follows. AV is equal to lambda times the identity matrix times V. The reason why I do this is that now I want to manipulate the expression as follows. I have AV minus lambda times the identity V equals 0. But now I wrote V times a matrix here and V times a matrix here. So by the distributive law, I can factor out V and write A minus lambda I times V is equal to 0. In other words, to find eigenvectors, we want to solve the linear system A minus lambda I x equals 0. Eigenvectors are solutions of a certain homogeneous linear system. Said yet again differently, the set of eigenvectors with eigenvalue lambda, so the set of vectors such that AV is equal to lambda V, is nothing but the null space of the matrix A minus lambda, the identity. Since this space of eigenvectors is identified with the null space, it is indeed a subspace because the null space is, and we call this an eigenspace corresponding to the lambda eigenvalue, or when I want to be brief, I'll just call it the lambda eigenspace. Let's revisit the example from the past video in light of what we know now. We knew that the eigenvalues there were 3 and minus 1. So when lambda is equal to 3, I can look at the matrix A minus 3i, which is given by the following. It's negative 2, 2, 2, negative 2. The way I got this matrix is by computing A, which is 1, 2, 2, 1, minus 3 times the identity. 1, 0, 0, 1. And if you perform this sum, then you get exactly that the matrix is minus 2, 2, 2, minus 2. So what we need to compute next is to find the null space of that matrix. And that will give us a description of the eigenvectors. In particular, we know how to find a basis for the null space of a matrix. So let's do that. To find the basis for the null space of a matrix, I need to solve the corresponding homogeneous linear system. In this case here, I can just do the row reduction in one step. If I add the two rows together, the second one disappears. And the first one, I can divide it by minus 2 to get minus 1, 1, 0. So that's my row reduced echelon form. In other words, solutions to this system as a free x2 and x1 is equal to x2. So when I write this solution as a vector, this vector becomes x2 times coefficients 1, 1. This fits exactly what we found last time in that we saw that 1, 1 was actually a 3 eigenvector. And by this computation here, we now know that 1, 1 is a basis for the 3 eigenspace, and in particular, the null space of A minus 3i, which is the eigenspace, is the span of the vector 1, 1. We can do a similar thing for the other eigenvalue that we saw last time. The eigenvalue was minus 1. We found one eigenvector, which was 1 minus 1, such that matrix multiplication flipped it over. So to make sure that the null space well, the eigenspace is actually generated by 1 minus 1, we can do the following. Again, as before, we have 1, 2, 2, 1. This is the matrix A, plus 1 times the identity matrix. I should do minus 1 times the identity. This matrix becomes 2, 2, 2, 2. Now, we could solve the homogeneous system as before, but in this case, one can observe immediately that taking the first column minus the second is the only possible solution to the homogeneous linear system. So one can observe that all of the solutions of the linear system, of the homogeneous linear system, are just the span of the vector 1 minus 1. I'm being fast here, but if you want to check the details, you can do it as before. Let's do a couple more examples in which we don't know, we're not just confirming an answer we know, but we'll find something new. Here's a matrix and a given eigenvalue lambda equals 1. We want to find a basis for the one eigenspace. The eigenspace corresponding to 1 is nothing but the null space of the matrix A minus lambda, the identity. Lambda in this case is equal to 1. So the first step should be to compute A minus 1 times the identity. When I do that, I have to subtract 1 from all the entries on the diagonal. So I get 0, 2, 0, minus 1, minus 2, 1, 0, 1, 0. Now we want to find the null space of this matrix. To do that, we solve the linear system associated with that matrix, which is given by the following: 2, 0, minus 1, minus 2, 1, 0, 1, 0, and then there's zeros here. When I start doing row reductions on this matrix, well, I find the following. I should move the second row to the top and maybe multiply it by 1. And then the other rows are just 1, 0, 0, 0, 2, 0, 0. So I can be done immediately by eliminating the 2's at the top and at the bottom with the 1 that I have on this row, and it's the only entry. So allow me to just do that and not rewrite the matrix so that we get this matrix here at the end. We have zeros on these two sides, and that's the reduced row echelon form. From here, we see immediately that X3 is free, and the null space of A minus I is generated by, well, let's see. X3 is free, and every solution looks like X3 times 1, 0, 1. X2 has to be equal to 0 by this equation. So the span here is by 1, 0, 1. And you're welcome to check, if you want to make sure of this, that the vector 1, 0, 1 is actually an eigenvector for this matrix. In fact, we can observe it immediately if you multiply the matrix 1 minus 1, 0, 2 minus 1, 1, 0, 1, 1 by 1, 0, 1. The effect of this vector is to add the first and third column together. And if we do that, you get 1, 0, 1. So the vector is not changed. In fact, it's multiplied by 1. Let's have a look at another example here. This time the eigenvector is 3. So again, the first thing that we want to do, sorry, the eigenvalue is 3. The first thing we want to do to compute eigenvectors is to consider the matrix A minus 3 times the identity. And this matrix has zeros here, and then there's a -2, 2, 2, -2. When I row reduce this matrix, I get 0, 1, -1. I take the third row, bring it up at the top, and then divide by 1. And then I can add the first and second row together. So the second row, when I add the third to it, becomes a row of zeros, and the third row also becomes a row of zeros. So the null space of the associated linear system, which would be the homogeneous linear system with added a column of zeros here, has the following solutions. There's only one pivot, which is it's just corresponding to the second column. So we have that x1 is free, and so is x3, and x2 is equal to x3. In other words, any solution to the homogeneous linear system looks like x1 times 1, 0, 0 plus x3 times 0, 1, 1. So the 3 eigenspace, which is the null space of A minus 3 times the identity, has a basis 1, 0, 0 and 0, 1, 1. I will write that it is the span of the linear independent pair of vectors 1, 0, 0 and 0, 1, 1. We could check that, for example, the 2 vectors we found are indeed eigenvectors for the 3 eigenvalue. In fact, if I take A times 1, 0, 0, this multiplication extracts the first column of A. So this is the same as the column A1, which is nothing but 3, 0, 0, which is 3 times the vector we started with. Similarly, if I take 0, 1, 1, this vector adds together A2 and A3. But if I do that sum, and I add the second column and third column of A, I get 0, 3, 3, which is 3 times the initial vector. This is 3 times 1, 0, 0, and this is 3 times 0, 1, 1. So those 2 vectors are indeed eigenvectors of A. In the next video, we'll start thinking about how to actually compute the eigenvalues. In this example, we started assuming that we knew what the eigenvalues were. Next time, we'll learn how to compute them.